So when dealing with kinematics questions where suddenly we have the idea of up and down involved, you have to establish a framework for what things are positive and what things are negative. So generally, when doing a question, like a vertical type question, because we have a grasshopper leaping upward and then falling under gravity, generally we choose upward motions as positive and any downward quantities as negative. So I'm gonna pop that up here, that up is positive. So if I go through these variables, then I have 5 grams. So my mass is 5 grams, which happens to be 0.005 kilograms. And I have a 10 centimeter dandelion. So if and you have your flower, I guess that's what a dandelion could look like. If the flower is 10 centimeters and this grasshopper makes a mighty leap upwards and then lands on the ground later, the net distance it's traveled is 10 centimeters below where it started. So since I've decided that upward distances are positive, if this grasshopper is now 10 centimeters lower than where it started, I need to use a negative. So the distance at the end is going to be negative 10 centimeters, which is negative 0.1 meters. Lovely. Now this phrase, falls to the ground. So you could make this complicated and throw in some air resistance, etc. But just to keep things easy, anytime something is falling, so free falling, right? It leaps and then it lands somewhere else without spreading its wings or doing anything complicated. You may assume that it's accelerating under Earth's gravity. So the acceleration due to gravity near the surface of the Earth is negative 9.8 meters per second squared. And I am using the negative because gravity is pulling you downwards. So I have a positive mass, a negative distance, a negative acceleration, and I need a time in there. So let's and falls to the ground, landing 2 seconds later. So I have a time now. Oops. Time of 2 seconds. So if I can get my cartoon off here. I, as always, need to find the remaining 2 kinematics variables as well as the force required to make this motion happen, and the change in energy from the start position to the final position for power output. So if I have distance, acceleration, and time, I'm missing the final speed, I'm missing the initial speed, and I still need force and I still need power. So I need an equation that connects final speed with time, acceleration, and distance. So I have this one. Distance is VFT minus 1/2 AT squared. So a distance of negative 0.1 meters. V final, which I don't know yet. Time is 2 seconds. Minus 1/2. An acceleration of negative 9.8 and a time of 2 seconds. So negative 0.1 is 2V finals. A negative times a negative is a positive, and half of 9.8 is 4.9. 2 squared is 4. Negative 0.1 is 2V final. 4 times 4.9, 19.6. So I'm going to have to subtract this from both sides. I'm going to subtract this over here. Negative 0.1 minus 19.6 is 2V final. So negative 0.1 minus 19.6 would be minus 19.7. And if I divide both sides by 2, I end up with 19.7 divided by 2, 9.85. Now, a handy way to check to see that if you've done everything correctly is when the grasshopper leaps upwards and then falls downwards, the final speed should be negative because it is heading downward. And we decided up there that positive quantities meant up. So if the thing is dropping, then its final speed should be negative, and that's what we ended up with. So that's good. We can pop that in there. Negative 9.85. I'm going to clear this up so we can do initial speed. So I need an equation that combines distance, acceleration, and time with initial speed. So that would be distance is initial speed time plus 1/2 AT squared. So using my distance of negative 0.1, an initial speed I don't know about, 2 seconds worth of time, an acceleration of 9.8 downwards, and a time of 2 seconds. Negative 0.1 is 2 initial speed. Now a positive times a negative gives me a negative answer. Half of 9.8 is 4.9. 2 squared is 4. And I have already forgotten what 4 times 4.9 is. 19.6. So I'm going to have to add this to the other side. So negative 0.1 plus 19.6 is 2v initial. That ends up being 19.5 is 2v initial. So divide both sides by 2. Initial speed ends up being 19.5 divided by 2, 9.75 meters per second. So this particular grasshopper leapt upwards from the dandelion. So again, we should check this number against our reference frame. It came out positive, and we've decided that upward actions were positive numbers. So in the text of the question, it does say that the grasshopper leaps this way. So that's good. It has leapt upwards because this is positive. So I can just pop that in there. All worked out. All right. Force, as always, is mass times acceleration. So in this particular question, I had a 5 kilogram grasshopper, or 5 grams, so that's 0.05 kilograms. Acceleration of negative 9.8. Force is 0.00005 times 9.8 negative is negative 0.049 newtons. Now, I have a negative there, so to interpret that, that means that the force causing this acceleration, this acceleration should be pointed downwards because it's a negative number. So I'm going to pop that in there. Negative 0.049 newtons. And to do my powers, I need to do the energy calculations. So energy, kinetic energy, 1/2 mv squared. If I do the initial energy first, I have 0.005 kilograms and an initial speed of 9.8 0.75 meters per second squared, which gives me 9.75 squared is 95.0625 times 0.005 is 0.4753 divided by 2 is 0.2377 if I round joules. So if I do the end energy, 1/2, mass is still 0.005, and the final speed is negative 9.85 squared. Now, a negative number squared is just a positive. So I have 9.85 negative squared multiplied by 0.005 divided by 2 is 0.2426 joules if I round. So my power output then would be the energy at the end, 0.2426, subtract the energy at the beginning, 0.2377, divided by the amount of time it takes, which we calculate, or we were given as 2 seconds. So 0.2426 minus 0.2377 is 0.0049, and divide that by 2. I get 0.00245 watts. And if you're a fan of metric prefixes, you could write that as 2.45 milliwatts. Let me pop that in there. There you go.